Greetings. So welcome to today's class. So let's briefly recap what we did in the previous class, and then we will move on to today's session. So we started off with our discussion on longitudinal dynamics, and we started off with braking, and we essentially did an analysis of drum brakes, wherein we wanted to look at how we can analyze drum brakes using simple lump models, and essentially get some insights into the operation of drum brakes, right? So we considered some approximations. That is, we wanted to consider cases where we lump the pressures, right, or the contact forces acting on the brake shoe into a single normal load NL. And then we consider the scenario when the brake has contacted the brake drum, and then we wrote down equations to balance the moments about the pivot. And then we calculated what was called as the brake factor, right, of the drum brake. Okay, so that's what we do. Of course, to be very precise, we calculated the brake factor of the leading shoe. So in today's class, let's calculate the brake factor of the trailing shoe, and then let's make some observations. So let me draw the free body diagram for the trailing shoe. The other shoe, which is part of the assembly, is the trailing shoe. So let me draw a free body diagram of the shoe. And then we will go ahead with marking the forces acting on the trailing shoe, and then let's do the analysis. So let's say this is the trailing shoe and this is the corresponding pivot. And once again, let's say F of A is the actuation force that acts on the trailing shoe. And then we lump all the normal load that is acting on the trailing shoe interface by a single force. Let's call this as NT. And the friction force mu times NT is going to be perpendicular to this. So consequently, we ask ourselves once again, what will be the direction of this friction force? So if we were to look at the diagram of the drum brake, and then if we reason out the direction of the force on the trailing shoe, the friction force on the trailing shoe, if we are looking at this point where we are lumping all the forces, please note that the deceleration torque should be produced on the brake drum in the clockwise direction. So that means that the brake force on the brake drum at this point, should be acting in the downward direction. So consequently, from Newton's third law of motion, the brake force, the friction force on the trailing shoe would be acting in the upward direction. Okay, so that's what will happen. So we go here, and then we go and draw the, we go and draw the, sorry about that. We go and draw the friction force acting on the trailing shoe. That's going to be upward like this. And this is going to be mu b times nt. Okay, so if we recall what was mu b was the brake friction lining coefficient, right? So I think, or the friction coefficient of the brake line. Okay, so these are the forces acting on the trailing shoe, and of course there will be the weight of the trailing shoe. So let's call that as mt times g, and there is going to be a restoring force from the spring. So let's call that as F spring. Okay, and once again we mark the other parameters as usual, right? So the dimensional parameters. So if we recall, we marked H, B, and A, right? So we are going to mark similar parameters here. Okay, so let's call this distance as H, the distance at which the actuation force acts from the point of the pivot. This distance is, let's say, H, and the distance from the pivot to the point where the friction force is acting. Let's call that distance as some A, and the distance from the pivot to the place where the normal load acts, let's call that as some B. Okay, so these are things which you are already familiar with. Okay, so this is the free body diagram of this trailing shoe. So let's write down the moments about the pivot and balance it. So balancing the moments about the pivot. Of course, we are going to neglect inertia, the weight of the trailing shoe, and the restoring force due to the spring and so on, right? So balancing the moments about the pivot, what do we have? So if we were to balance the moments about the pivot, we are going to get FA times H, that's going to be one moment due to the actuation force, minus mu B NT times A. Okay, that's going to be the torque due to the friction force, okay, minus Nt times B, okay, and this is going to be equal to I times alpha, but I times alpha we are essentially going to neglect as before, and so we can approximate it to be 0. Okay, so this is the same what to say principle we used to write down the equation for the leading shoe in the previous class, right? So that is the same idea that we are using. So here we can immediately notice that the moment we write down this equation, so there is no self-energization. Okay, so there is no self-energization in this case, and we can immediately see that the torque due to the friction force is in fact opposing the torque due to the actuation force. So consequently, we can also get a physical perspective, because due to the way in which the drum is rotating, right? So if you go back to this diagram, right? The way in which the drum is rotating, the friction force will tend to push the uh, trailing shoe away from the drum, okay? So that is why there is no self-energization. And that is the reason why this shoe is called as the trailing shoe. Okay, so I hope the reason behind calling this shoe as a trailing shoe is now clear. Okay, so why this shoe is called as a trailing shoe? Because in terms of performance, there is no self-energization happening in this trailing shoe. So now, if we were to get the expression for the normal load NT will now be FAH divided by B plus mu BA. Okay, so we can previously observe that the normal load was FAH divided by B minus mu BA for the leading shoe, right? Now it is the denominator has become B plus mu BA. Okay, so that is what has happened. So, and consequently, the friction force from the trailing shoe is going to be mu times NT, mu B times NT, okay, mu B being the brake lining coefficient. So this is going to be mu B FAH divided by B plus mu BA. Okay, so that's what we have, okay, as the friction force from the trailing shoe. So consequently, the brake factor, right, which is indicative of the ratio of the output from the shoe to the input to the shoe. So the brake factor from the trailing shoe, okay, which let's say we call this as BF subscript T, is going to be equal to mu B times NT divided by the input to the trailing shoe, which is going to be equal to FA. Okay, so consequently, this we will get it as mu B times H divided by B plus mu BA. So we can immediately observe something, right? So for the same brake friction lining coefficient and same dimensions, the brake factor of the leading shoe is going to be much higher than the brake factor of the trailing shoe. Why? Because if you look at the expression from yesterday's class, we can see this B minus mu A, right, coming in the denominator, right? Is it not? However, if we look at the expression that we derived in today's class, right, in the denominator, we have B plus mu A, right, appearing. So obviously this B plus mu A will increase the denominator and consequently reduce the break factor of the trailing shoe. Okay, so that's what is going to happen. So this implies that the break factor of the entire drum brake, okay, break factor of the drum brake is going to be equal to, let's say we call it as BF drum. So that's going to be the break factor contribution from the leading shoe, which is mu BH divided by B minus mu BA plus mu BH divided by B plus mu BA. Okay, so those are the two terms. Okay, so if you were to mark it very clearly, this is the contribution from the leading shoe, and this is the contribution from the trailing shoe. Okay, and that is going to be the total break factor of the drum brake. All right. So this is a very simple analysis for us to understand how this drum brake works and how one can quantify the performance of drum brakes. So now, in fact, if we go back to the same diagram that we considered, right? So now I hope it is clear why it is called as a leading trailing shoe drum brake. Okay. So now if we shift the pivot, okay, from this point to this point, okay, and then we apply the actuation force at the bottom on the right shoe, what's going to happen is that like we are going to get what is called as a two leading shoe drum brake. Okay, so you can see that just by swapping the pivot to the other end in the right brake shoe, keeping everything else to be the same and applying the actuation force at the bottom, will make it as a two leading shoe drum brake, then the brake factor is going to be pretty high. Okay, so we are going to get very improved performance, but there's a price to pay. What is the price? The price is that like we'll be requiring another actuator or wheel cylinder at the bottom, right? So the cost and complexity of the brake system would increase. Okay, so what is the alternative? So what now is being done is that like we use what is called as a duo servo brake, wherein these pivots are in fact placed in slots, right, to accommodate for any adjustment. And there is an adjustment mechanism which connects the two brake shoes. So we still have only one actuator, but then when the brake force is applied, okay, and the leading shoe gets pulled into the brake drum, this pivot will essentially tend to push the shoe at the right, okay, in this direction. So consequently, what will happen is that the rightmost shoe gets pushed from both directions, okay, into the drum brake. So consequently, it provides a better performance, right, in terms of brake factor when we compare it to the leading trailing shoe drum brake. So the bottom line is that like leading trailing shoe drum brake has the lowest brake factor, followed by the so-called duo servo brake. Okay, so that this arrangement is what is called as the duo servo brake, where we give the link at the bottom and then push it from both directions. Okay, and the two leading shoe drum brake will have the highest brake factor. Okay, so these are some concepts associated with drum brakes. Okay, but the important thing which we will be using is that we can notice that the brake factor of the drum brake is a non-linear function of the brake lining friction coefficient. Okay, so that is an important concept which we are going to utilize. Okay, so now having looked at drum brakes, any question on drum brakes before we go to disc brakes?
Sir, if we are using that pivot, then what is that shoe called? It cannot be the leading and it cannot be the trailing, right? Because we are applying actuating force from both directions.
Which pivot, So that is what is called as a two leading shoe drum brake. Okay, when the pivot is shifted to the top, okay, and there is an actuator at the bottom also. Okay, so that is what is called as a two leading shoe drum brake. Okay, and then what I discussed after that was what is called as a duo servo brake. Okay, where there is still only one actuator at the top, but then the adjustment mechanism at the bottom will push the right brake, okay, the trailing shoe, right, into the drum from both ends. Okay, so slightly better than the leading trailing shoe drum brake. Okay.
Yes, sir. That duo servo brake only. I'm just asking, like,
Hmm.
what is the mechanism of the right side shoe in that case? It cannot be the trailing or it cannot be the leading, right? It will
It will
be in
be
between.
it will be still called trailing shoe, okay, because the brake factor from that shoe will still be lower than that of the leading shoe, okay, slightly higher, but it will be still lower than the left shoe. Okay.
So by this brake system, can we conclude that the leading shoe will have a major contribution towards braking of a vehicle?
Yeah, the leading shoe is going to provide more braking force, right? Yeah, when compared to the trailing shoe. Right?
Mm. So even for then, leading shoe will wear more as compared to trailing shoe, right, sir?
Yeah, so one needs to take that into account, right, during the design process, correct? Yeah. So ideally, we want to make it as close as possible, but that's where the finer aspects of the design will come in, right? So
So even in the case of duo servo brake, the braking factor will be same for leading and trailing, right? Because in that case, both will be plus. Then denominator will both be plus in both the
Okay.
cases.
We will not be able to use this analysis per se for the duo servo brake because see what is going to happen is that the pivot per se is not fixed, right? So it is in motion and we are applying a significant force from the bottom also, right?
Okay.
So some other analysis needs to be followed. The bottom line is that like its brake factor is certainly going to be lower than, greater than what we derive right now today. Okay, like mu b h divided by b plus mu b. Okay, so once again, I should be very careful here. So we have derived these expressions just to get a sense. Okay, we have made a lot of approximations in deriving these expressions. Okay, so please keep that in mind. Okay, yeah. So in
Okay.
fact, there are brake design handbooks which will give us more accurate expressions for these for this analysis. I will maybe share those references with you. Okay. All right. Okay. Any other questions before we
Sir,
proceed? Yeah.
sir, when the car is going in reverse, right? This trailing and the leading shoes will get swapped, right? The trailing
Yes.
will become leading and
Mm, mm.
the leading will become trailing. So any observations there specifically based on this one, sir?
So, but then the point is that that's a good observation. But the point is, like if we look at reverse motion, anyway, we are not going to typically demand a very high braking torque, right? Yeah. So even if there is a swap, right? So we will still be able to get reasonable performance, right? So yeah. See, imagine reversing a car, right? So we are not going to do it at very high speeds and demand high decelerations from the brake system, correct? Yeah.
Yeah. But for slow moving vehicles and all, right?
Mm.
They will be used almost in the same speeds, both in the forward as well as the reverse directions, like an
Yeah.
earth mover or some
Mm.
off-highway vehicle, like a
Mm.
tractor or something.
Mm.
So that's where I was thinking about. But anyway,
Ah,
for those vehicles, the brake mechanism by itself is different.
different, exactly, right? So the braking
Okay.
mechanism itself is different. You are right. Next, so we are only considering road vehicles, right? So on road vehicles where we have these friction brakes, right? So
Okay, sir. Thanks.
okay, yeah. Any other questions? All right. Okay. So let's then move on to the disc brake. Okay. So once again, we are going to do very rudimentary analysis, right? So to get some key concepts understood. Oops, sorry. We will essentially look at a simple schematic of a disc brake and then do a similar first cut analysis, right? So to compare it with the drum brake. Okay, so this is just a simple schematic of a disc brake. So what happens is that now we are looking at the vehicle, let's say from the front, there is a rotor which rotates along with the wheel assembly. Okay, so this is the rotor which is rotating along with the wheel assembly. And then what we have is that we have this caliper, okay, caliper assembly, which is supported on support blocks. And we have on both sides of the caliper assembly, we can see these brake pads, right? So we can see one brake pad in this direction. So this is the caliper, and this is one brake pad, and we can see another brake pad here. So what happens is the following. So when the brake is applied by the driver, and considering a hydraulic brake, the pressurized brake fluid will enter into this cavity and it will act on this piston. Okay, so the fluid pressure acts on this piston. The pressure is converted into an actuation force, and that pushes this brake pad against this rotor. Okay, it will go and clasp the rotor. Okay, so that is what is going to happen. At the same time, this pressure is going to act on the other side of the caliper, and consequently the entire caliper housing will slightly move to this side. And then what will happen is that this brake pad will come and clasp the rotor from the other end. So we can imagine, let's say, the two brake pads clasping, right, the rotating rotor from either end. Okay, so that is what is going to happen in the case of a disc brake. So in a disc brake, the motion of the braking element or the friction element is going to be axial, right? It's going to happen along the axis of the rotor's rotation, right? So now if we look at it from the side, let's say that's our wheel, and let's say this is a very simple visualization of the disc brake. So what is going to happen? So let us say this is our disc brake. Now, without loss of generality, let's assume that the wheel is rotating in the counterclockwise direction. And let us say we push the brake on the wheel, on the rotor, right? The friction force will be equal to mu b times n. Okay, so where n is going to be the normal load, which will act on the at the interface between the brake pad and the rotor, right? So I'm sure all of us can understand how we got this. So n is the normal force that acts at the interface between the brake pad and the rotor, and mu b times n will be the friction force, right? So that will act on the rotor, right, due to the braking action. Now, at steady state, what's going to happen? So when the brake has been applied and the rotor, the brake pad has gone and clasped the rotor, what's going to happen is that the normal force acting on the brake pad is going to be almost equal to the actuation force, right? Imagine that, we have applied the brake. Okay, so the brake pad has gone and clasped the rotor, and braking is progressing at steady state. So whatever actuation force that we apply will be the normal force that will be experienced, right, at the interface between the rotor and the brake pad. Okay, so that's what we'll have. So consequently, the brake force, the friction force, right, on one shoe or one pad, right? So brake force from one shoe or one pad is going to be equal to mu times n, which will be mu times Fa, right? So once again, we are doing a very lumped first cut analysis. So consequently, the brake factor of one shoe or one pad is going to be the following. Okay, that's going to be equal to mu times FA, which is the output, divided by the input, which is FA itself, right? Or sorry, we are calling it as mu B, right? Sorry about that. So please put the subscript B to indicate that we are dealing with the brake friction coefficient of the brake line. Okay, sorry about that. So we write this as mu B. So this is approximately equal to mu B. Okay, so that is the brake factor of one pad. So this implies that the brake factor of a disc brake, assuming that it has two brake pads, right, one on each side. So the brake factor of a disc brake, right, is going to be approximately 2 mu B. Okay, so 2 times mu. All right. So if we look at the brake factor of a drum brake, which is mu BH divided by B minus mu BA plus mu BH divided by B plus mu BA, right? And the approximate uh, brake factor, right? So of a disc brake, which is 2 times mu B, we can in fact immediately conclude that for typical brake dimensions, right, the brake factor of a drum brake is much greater than the brake factor of a disc brake. Okay, so that is something which is a given. So the brake factor of the drum brake is greater than the brake factor of a disc brake for the same value of mu B. Same value of the brake friction lining coefficient. The brake factor of the drum brake is going to be greater than the brake factor of the disc brake. Okay, so then the question arises, why are we using disc brakes? Okay, so nowadays, you know, like if you go for, let's say, a high performance vehicle, right? So if budget is not a constraint, right? So one would tend to go for you know, like all disc brakes, right? Why? Sorry, that's the usual choice. But then based on this discussion, one would try to go for all drum brakes, right? Why? Because in a broad sense, the brake factor is nothing but the friction force output or the brake force output divided by the actuation force input, right? Is it not? So divided by the actuation, sorry, divided by the actuation force input. All right. So this is the brake factor, and consequently, you know, like we can immediately see that if a brake has a higher brake factor, I should be using that, right? So, but then we typically go for using the disc brake, right? Why do you think that is the case?
Weight of the brakes is one thing, sir.
Okay, so if you look at the weight of the brakes, disc brakes typically weigh more, right? So even drum brakes are much more compact, you know, like and take up what to say, can be fitted more easily within the wheel hub, right?
Sir, because of the surface area, like whatever we are applying the pressure, sorry, contact.
So what about surface area? You know, like
Yeah, there is a point contact kind of thing, right? Like on the drum brake. Here in this brake,
so but
there is
then like no, that is an approximation. Okay, so okay, let me clarify. Okay, so the fact that we essentially are considering the for the purpose of analysis, right? We are essentially considering a point contact, right, for the drum brake as well as the disc brake. Okay, yeah.
okay.
So, but then in real life, anyway, both are going to have some contact over an area, right? So that is understood, right? So
Yeah, sorry.
yeah, that's fine. You know, so I think we are discussing openly. You know, like just trying to see. See, because this is a very important thing, right? So that was also my primary motive of doing this very simple analysis, right? So if you go for, let's say, a high-end car, right? So today, everyone will be putting in all disc brakes, right? So, but then like, you know, based on this analysis, we should be using all drum brakes, right? So why are we doing that. Okay, so that is something which I wanted to illustrate through this simple example. So simple exercise. Okay, so now let's plot the variation in the brake factor with mu b for both the disc brake and the drum brake. Okay, so once again, I'm going to do a very qualitative analysis. Okay, so I'm just going to draw some representative figures that essentially show how the brake factor vary for a disc brake and a drum brake. Although it is true that the brake factor for a drum brake is much higher than, the brake factor for a disc brake, the variation, is going to be a non-linear curve. Okay, so for a drum brake. Okay, so that's how I am just drawing an approximate curve. Okay, so this is the brake factor plot for a drum brake. Now, if I were to draw an equivalent diagram for a disc brake, okay, so it's going to be almost linear. So this is going to be the brake factor of a disc brake. So now let us say I consider a fresh brake friction lining, okay, so which essentially has an initial brake friction coefficient of some mu I, okay, and consequently the corresponding brake factor of the drum brake and the brake factor of the disc brake are here. Okay, so we can immediately see that the brake factor of the drum brake is going to be much higher than the brake factor of the disc brake. Okay, so that's something which all of us can understand. But then what's going to happen with usage, you know, like see, with when we start using the brake system, there is going to be wear and tear of the friction lining, point number one. And then the brake linings also get hot, right? When the brake lining gets hot, the value of mu is going to drop. And consequently, what will happen is that the value of, the brake factor also will drop, okay, as evident from this figure. So let us assume that just for the sake of argument, let's say that, you know, the value of mu has dropped by this much. Okay, so this is some delta mu. All right, so that is the reduction in the brake lining friction coefficient due to, let's say, wear and tear, you know, like or thermal temperature increase and so on, right? So if that is the case, we can immediately observe that the brake factor of both the disc brake and the drum brake will drop. However, we can immediately observe something which is very interesting, right? What can we observe? The decrease in the brake factor of the drum brake, which is this. Okay, so if we call it as delta BF drum, is going to be much larger than delta BF disc, okay, which is the decrease in the brake factor of the disc brake. Okay, and so that essentially gives us a very interesting observation, right? So typically during operation, we are going to encounter what is called as brake fade. What is brake fade? Brake fade is essentially a reduction in the friction properties of the brake lining due to the temperature increase. Okay, so if you were to put it in very simple terms, it is a decrease in mu b with increase in temperature. Okay, so that is one reason. And anyway, when the brake pads or linings undergo wear and tear, their friction properties are also going to change, and that's also going to further lower the value of mu b, right? But then we can observe that the sensitivity of the drum brake, okay, to a reduction in the brake lining friction coefficient is much higher than the sensitivity of a disc brake. Okay, this is what is called as mu sensitivity. Okay, in the context of friction brakes, you know, like when people talk about mu sensitivity, they are talking about the sensitivity of the brake output, right? So with respect to variations in mu b. Okay, so this mu sensitivity is higher in drum brakes. Okay, and that is a disadvantage of a drum brake. Okay, so if we look at it from another perspective, although a drum brake will give higher brake friction force output for the same actuation force under similar design conditions, when the brakes get hot, okay, or due to whatever reason the value of the brake friction lining drops down, the performance of the drum brake is going to deteriorate to a larger extent when compared to a disc brake. And that is the reason why, if cost is not a constraint, one would want to go for all disc brakes, okay, in both the front wheels and the rear wheels. All right, so I hope that point is clear. So the disc brakes give better performance, more reliable performance, right, than drum brakes from this perspective. And this is extremely important because, as we discussed, the brake system is the single most safety system which is available under the control of the driver, right? If the brake system deteriorates significantly, like we are going to have issues, right, in regulating the vehicle, controlling the vehicle. So we have to be careful about that. Okay, so and another advantage of disc brake, which is also a positive thing about them, is that the way they are mounted, right? Drum brakes are, if we have looked at drum brakes are very compact. The brake drum and the brake shoes are one self-enclosed compact unit, and they are in turn mounted within the wheel hub. So consequently, the chances or the heat dissipation characteristics, okay, of drum brakes are relatively poorer when compared to disc brakes. Because the way disc brakes are set up, we can immediately observe that the brake pad is going to contact the rotor over a small area, right, over here. And when the rotor rotates, this area which is going to be hot will move, and consequently that will be exposed to flowing air, which can lead to better heat dissipation, right? So due to all these multiple reasons, disc brakes have better heat dissipation characteristics. So what is the impact as far as physical application or practical application is concerned? Not only is a disc brake less sensitive to change in mu, given the same operating condition, the delta mu in disc brakes will be lower to begin with. Why? Because disc brakes will be able to dissipate the heat energy, which is a result of friction braking, and it will ensure that the value of mu b will not reduce by a large extent when compared to the drum brake in the first place. So whatever argument we have put forth was assuming the same delta mu, right, for both the disc brake and the drum brake. Even if we have the same delta reduction, okay, between the disc brake and the drum brake, we can see that the disc brake is still better, right, in terms of having lower reduction in performance. However, it so turns out that disc brakes also have another advantage, is in the sense that, like the delta mu will be lower to begin with because of better heat dissipation characteristics. Okay, so that is why we tend to use disc brakes on all four wheels if cost is not a constraint. Main limitations of disc brake is that, like, we require a higher actuation force to get the same brake force, right? Why? Because the brake factor is lower, right? If you want higher actuation force, what is required? We require either higher actuation pressure or a higher sized actuator. So actuation pressures are what they are, right? In the hydraulic brake system, considering a hydraulic brake system. So we have to go for a higher actuator, a larger actuator. Larger actuator means the size of the disc brake will be larger, right? So disc brakes are relatively bulkier, they weigh more, so they are larger in size, but then they have these advantages. Okay, so that's why we tend to use them. So the most common configuration we will see in passenger cars, in most classes of vehicles, right? And neglecting the very low-end vehicle where we'll have all drum brake due to cost constraints, and neglecting the high-end variant where we will have all disc brakes due to better performance, would be the configuration where we have disc brakes on the front and drum brakes on the rear. Why do you think, based on this discussion, that configuration is very popular? Disc brakes on the front and drum brakes on the rear.
The engine compartment is at the front, so heat will be more in the frontal brakes than the rear one. So heat
Okay.
dissipation is required more in front than the rear.
Okay. Okay. So let me put it this way. Suppose, let's say we are essentially currently not considering the thermal load due to the engine. Okay. Just based on this analysis, whatever we have discussed, right?
Sir, for the front wheels, usually it will be a front wheel drive car. So these wheels will be, the axle will be driven by the engine directly, and the one in the rear will be a dead axle. Maybe that's one reason I'm guessing.
Okay, so I think your responses seem to be from the perspective of the powertrain layout or the placement of the prime mover and so on, right? So, but based on what, just from a pure braking perspective alone, yeah, I do agree that other factors also will play a role, but from a braking perspective, what do you think would be a reasonable set of reasons?
Sir, when the braking is usually done, the weight of the vehicle used to come to the front, right?
Yes.
When the weight transfer happens to the front axle, the reaction of the front wheels will go up. So they will tend to slip less than the ones in the rear end.
They will tend to slip less than. Okay, fine. Okay, so I think very good. Like we are going to do that analysis. However, we will do that analysis, and then like we will build more on that argument. But that's a good point. There are two reasons, right? So, or there are multiple reasons. Let me articulate them carefully. So let's say in a typical passenger car, which wheels are loaded more? Which wheels will have more load?
The front wheels.
Front wheel.
Front wheels, right? So typically the engine, the powertrain will be mounted in the front. So consequently, the static load on the front wheels will be higher than the static load on the rear. Okay, so that's point number one. So higher the normal load on a wheel, more is the braking capacity. Okay, we will be doing the braking dynamics in the next, starting with braking dynamics analysis in the next class. So higher the normal load, more is the braking capacity. So we get more braking capacity in the front wheels. Point number one. And as our friend correctly pointed out, we will once again realize it through our analysis. When braking is done, there is going to be something called as longitudinal dynamic load transfer. Okay, from the rear wheels to the front wheels. I'm sure all of us would have experienced it, right? So suppose, let's say we are going in a bus, standing in the bus, and then like the bus driver applies the brake suddenly, right? What happens to all of us? All of us tend to go forward, right? So that means that, there is going to be a dynamic load transfer along the longitudinal direction from the rear wheels to the front wheels. So during braking in a typical passenger car, not only is the static normal load higher on the front wheels, there is an additional component that is added on to the front wheels due to dynamic load transfer. So the net effect is that there is more load available on the front wheel for braking. So let us say due to dynamic load transfer, there is a 70-30 normal load distribution. Then that means that 70% of the braking can be done by the front wheels, 30% can be done by the rear wheels. So we want that 70% to be very reliable, right? So we can't afford a reduction in that 70% due to brake fade and other phenomena. That is the reason why we go for disc brakes on the front. However, in the rear, anyway, we are going to have a lower component of braking or lower proportion of braking. So consequently, although it is not the ideal scenario, but given a constraint that, we need to put in disc brakes on one set of wheels and drum brakes on another set of wheels, the configuration which will have the least trade-off will be putting the drum brakes on the rear. Okay. And another advantage of drum brakes on the rear is that like these mechanical parking brakes also can be easily integrated in a drum brake. Okay, so that also makes it very attractive, right, and cost-effective solution to put the drum brake in the rear wheels. Okay, so these are some reasons why most brake configurations in passenger cars use disc brakes on the front and drum brakes on the rear. All right, so I hope this reasoning is clear. Okay, any questions? Okay, so in tomorrow's class, we will be looking at braking dynamics in great detail, but let me just start with a brief explanation of what we are going to do as far as braking dynamics is concerned. So when we are going to study braking dynamics, we are going to study the response of the vehicle to the forces applied through the brake system and the other forces that act on the wheels, and how these forces are related to the acceleration and the motion of the vehicle. Okay, so that's what we are going to do. Okay, so when we look at braking dynamics, like what are the loads or forces that act on the vehicle? So loads are nothing but the forces, right? So essentially that act on the vehicle. These include inertia, okay, which is going to be m times a, and we will have aerodynamic drag, so which is going to be felt by the vehicle. So that's going to be a resisting force. And then like we will have rolling resistance. So we look at all these forces. Okay, so rolling resistance is caused due to the viscoelastic nature of the pneumatic tire. So there is an energy loss due to that, and that is quantified using rolling resistance. So if we are going up a grade, there is going to be a grade resistance W sine theta, which acts on the vehicle. And then like if we are pulling any other entity, right, using our car or using a vehicle, we are going to get what is called as drop output. Okay, so these are all the various loads that act on the vehicle and basically affect the braking response. All right, so we will, when we analyze braking dynamics, we are going to look at models that will essentially relate all these forces and relate them to the motion of the vehicle. Okay, so that's what we are going to do in the next class. All right, okay. So I will stop my discussion here for today's class. Any questions before we close this class? All right, so if not, let me stop recording. Thank you.